So, hi all. This is my great pleasure to introduce Professor Asher Lawson from the INSEAD University. His research examines bias in human decision making and develops targeted interventions to improve judgment. He focuses on debiasing numerical estimates and on using large language models, which I think he will talk about today, to better understand decision processes. Asher is a bright young scholar who has already managed to publish in some of the very top journals, including PNAS, Nature Communications, and much more. Last but not least, Asher is an avid reader. Talk to him for a bit, and you will be amazed at the sheer range of books he has read. Uh, Asher will proceed as follows. You will have about 45 to 50 minutes for the presentation,
Is it only
and then
me or
about
everyone?
the whole part will be over, and we will stay additional 15, 20 minutes. What do you mean?
We
Yeah, we
we
could
had
we couldn't hear
less
you, I think.
the end
Oh,
of your thing was less clear. So what you basically says that Asha has 45 minutes for talks and question, and then maybe informal meeting.
yes, and we are very sorry for the some technical issues. Usually it's not the case, but it is what it is. So, Asher, the floor is yours.
Okay, thank you, Yefim. So my understanding is this is it's his internet, not my internet. So I'm going to proceed talking as normal. If you have a problem with my audio, please
I
let me know.
assume you don't hear me well, but Asher, the floor is yours.
Okay, thanks, Yefim. So for this lovely introduction, which unfortunately got cut in the middle just when Yevon was complimenting me on my reading taste. So that's a shame that you all missed out on, but I'm a big fan of Dostoevsky, as Yefim learned after a beer too many in Fontainebleau. But delighted to be joining you remotely from Paris to talk about this work on psychologically interpretable differences in decision making under uncertainty. Special thanks to everyone for taking the time to make it regarding everything that's going on. I'd like to start before I get into the research with a little bit of the personal history of this work. So here we're going to zoom back all the way to Society for Judgment and Decision Making 2018. This was my first ever academic conference in November in New Orleans. I had the pleasure of watching Ori give this talk, which I dug out of my Apple photos, which I believe may even have been the CPC 2018 results, which he somehow managed to present again at SJDM 2025. I think maybe enough time had passed that people had forgotten. So since then, it's going on 7.5, 8 years. I'm trying to think of something to do in this space where I've really captivated by the model, by the behavioral tendencies, by the predictive results, but it's been a journey working out where I can contribute something here. And so I wanted to start off with this positionality statement to say a couple of things. First is that we'll be building heavily on this work. And second, to say, I'm not saying these things to compliment Ido or Ori or anyone else. I'd say the same stuff if they weren't there. I just have the added awkwardness of them being in the room. So we're going to think about how can we extend Beast? How can we build on the work that they've been doing to get some unique psychological insights? I'm also going to assume that everyone in the room has at least some familiarity with this work or with this vague area of research, and so I may move a little bit quickly if that assumption is wrong. I think as the Yefim said, I have something like 45 minutes to talk, where I'm very happy to take questions, clarifications, interruptions at any point. I am not looking at the chat or anything, but I'm looking at these videos, so you can put your hand up or just start talking. Be happy to have this be a conversation rather than necessarily just presenting straight. And so the motivation for this work, if we think where descriptive models are in studying decision making under uncertainty, there are two main errors, shortcomings, something like this we can say. The first is that they only capture some paradoxes. So you can have specific models that are developed to explain something like the reflection effect, then you give them another paradox, and they're not able to explain the two of them together. At the same time, if you think about what do they teach us about decision-making processes, you can have all of these parameters, but they're not really telling us something about what those individuals actually do when they get into facing that choice. Is these rely on this as if locution where it's capturing general tendencies and how people are making decisions, but not really explaining to us how they're doing that. It's the fact that people are sensitive to losses. Does that mean they're spending more time looking at them? What does this actually mean for someone who's sat there facing a decision? And so in response to this and other points, you have the work of CPC 15 and CPC 18 thinking about approaching studying decision making under risk from a different perspective, where we think instead of something like prospect theory that's firmly rooted in expected utility theory, we can think of how can we evaluate the attractiveness of different choice options, different prospects from the perspectives of different heuristic tendencies. And specifically, the four behavioral tendencies included in the BEAST model, which has since been adapted in various ways, are the following: pessimism, meaning when we have ambiguity, people's tendency to evaluate expected value with pessimism, as well as heuristic forms of valuation. So what is the expected value of an option if you just equally weight the outcomes rather than probability weighting them? People being sensitive to the sign of the outcomes they can receive, as well as people minimizing regret. And so, simple example of that, if you want to think what choice should someone take if they're aiming to minimize regret, you want to think about the option that leads to the better outcome most of the time. So the probability that that outcome will lead to a superior realization. This is one perspective one can take in trying to think about the attractiveness of different prospects. And so there's two reasons why I think this model is an attractive basis to start with and thinking about trying to understand further the psychology underpinning risky choice. The first is its predictive accuracy. So I've taken this graph from a recent 2025 paper. You can see at small or at large levels of data, having a lot of choices available to you, you can see models based on these BEAST features. So this is BEAST gradient boosting, had this very low mean squared error relative to something like prospect theory. Even when you do a fancy version of prospect theory where you need a lot of data to fit more complicated functional forms, you still see it's converging to a degree of mean squared error. It's something like more than 2 times, I don't know, maybe 3, 4 times the mean squared error. So if we want to get a really good behavioral model that's capturing a lot of the tendencies people exhibit across a broad range of scenarios, having something that has that predictive accuracy is a good basis. The second reason why I find this model appealing is the fact that it can get us more within these layers of how Mar categorizes cognitive processes. So if you're not familiar with these three levels, something like prospect theory is really only looking at the computational level of what people are doing. People might act as if they are loss averse, but it's not telling us about the specific representations they hold, the processes that they follow to then produce choice behavior. Whereas something like BEAST that instead has these biased sampling tools. So what happens if someone looks at a prospect and just thinks about equally weighting the outcomes rather than probability weighting them? I'm not taking the view that this does achieve this algorithmic level. I don't think that we have the evidence yet for that, but at least has the potential to. Because these tools capture something someone could do while looking at a choice in a way that is not possible in these things orientated around expected utility theory. So for these two reasons, I think that this approach is very promising for trying to understand more deeply the actual decision processes people follow when looking at decision making under uncertainty. But specifically today, I'm going to build on the work they've already been doing to think about the question of individual differences. There are many reasons to expect why we will observe individual differences in the tendencies people exhibit in risky decision making. If you look, there is direct evidence. In other functional forms, you take something like expected utility theory and you estimate coefficients of risk aversion, something like this, there is evidence for individual differences. You also have scales like Dosbert that show you can think of risk-taking as a psychological trait, albeit it looks as if it's context dependent, meaning that it varies across different domains. In addition to this direct evidence, there's a whole host of indirect evidence. So you can think about the fact that numeracy, cognitive reflection affect all types of tendencies we might think are associated with decision making under risk. So directly risky decision making, but also statistical reasoning, overconfidence, people's susceptibility to framing effects. And there's other work thinking about the fact that people can be better fit by different models. together, all of this existing research suggests that we should observe individual differences in the decision-making tendencies under risk. And we can use this BEAST framework and its high predictive accuracy to try and unpack these to make some more psychological insights. And so today, I'm going to be primarily describing the results of one study that I've ran that is a complicated study, so hopefully it will fill the time all the same, that uses the features of BEAST but builds on them in this specific fashion. But we take the features, so this is the 2017 paper Ori headed up of moving beyond the sort of more process-oriented BEAST implementation to think about those features, and we'll come to exactly what I mean by that in a minute. We're then going to use them in a mixed effects modeling framework where we can look for individual differences in the extent to which people are sensitive to these properties just by modeling them as random slopes. And then once we have these random slopes, or I'll call them individual sensitivities, capture the extent to which different individuals are sensitive to this property of the prospect, we can then think about, sorry, someone entering the room's distracted my cursor. Once we've estimated those individual sensitivities, we can go beyond that, trying to psychologically interpret them in terms of relating them to other individual differences in cognitive processes that we know. And so I think this is an ugly formula to show, but it helps to give some concreteness to what I'll be doing, which is looking at formulae like this, where we have a whole bunch of fixed effects that capture general tendencies in how these different properties of decisions affect people's likelihood of choosing one option over the other. But we fit these specific random effects that can capture these individual sensitivities, meaning the general way in which an individual responds to different properties of the gamble. So I'm going to stop at this moment, just if there are any questions about the approach or the high level what we're trying to achieve in fitting these individual sensitivities before I get more into the implementation of how I actually approach this.
Just to make sure that I understand, you're talking about decision like risky decisions. That means like decision from description that you know all the probabilities and outcomes, right?
So I'll come to specifically what I did in a moment, but this is building on the problem space that they built for the choice prediction competition. So this 11-dimensional space, which is from description to the extent that things are written, but it also contains choices with ambiguity. And then today I'm just going to be talking about the one-shot case rather than looking at receiving feedback. So those ambiguous ones will stay entirely ambiguous.
So my question is, if it's an ambiguous gamble, do you still can get into your formula the outcome and probabilities, although the subject, the participant, the decision maker does not know it?
Yeah, so they're still seeing some information. In my data, the ambiguous decisions are a relatively small part of it. So for the most part, you can think that we're talking about fully described gambles.
Okay, thanks.
Thanks.
I have two questions.
Yeah.
One, I see that the random slopes is a subset of all the fixed effects. So how did you choose which one to put as random slopes? And the second question is that did you consider interactions between the features in the fixed effects part of the model?
So on the first question, I'm going to wait a moment because this is what I'm going to get into describing next. On the second question, I did not for now. I don't think it would capture much of the random slopes that I'm going to be emphasizing. It could be possible. I suppose the fact, if you look at the work they did in CPC 18 and so on, the fact that sometimes these machine learning algorithm ways of combining these features achieve superior predictive accuracy, there must be some interactions in there. But it's not something I've included in these functional forms.
Thank you.
Thanks. All right. Then I'm going to move on to getting into the details of exactly what I did. So I took the features of BEAST. So this again is just taken from the recent 2025 paper, which include these basic properties of the gamble being described. So what are the different payoffs people can receive? What are the different probabilities of those payoffs? What is the shape of the probability distribution? Is it ambiguous or not? These are the basic features that just characterize the problem, context, as well as these naive features that capture basic things one might compute or look at without having any sort of psychological response or behavioral theory. These are all just included as fixed effects. For what it's worth, if you add random effects to these features, you don't get any extra predictive power, really. It actually is on the psychological features that we'll come to in a second where it looks like the random effects are important. But for here, you can just think of these as fixed effects we're including to account for all of those characteristics of the problems being considered. But it really comes into our own, and what I'm going to be focusing on today is thinking about the psychological features included in BEAST and individual sensitivities to those. So I'm not going to go too much into the details of all of these, but just to say that there's, I want to say 9 different features here that capture those 4 main behavioral tendencies we discussed, as well as some additional adjustments that cover more edge cases or specific parts. So this first point deals specifically with pessimism, thinking about what is the expected value of the gamble under ambiguity with pessimism. And you have 2 features that are capturing equal weighting. So what is the difference in EV between the 2 prospects if you equally weighted them, as well as what's the probability of receiving a better outcome if you assume equal weighting. So then 2 features that capture people's sensitivity to signs. So the equivalent things of equal weighting of just focusing on the signs, as well as this minimizing regret, which is the probability of receiving a better outcome in one gamble than the other. These are really the 4 main sets of behavioral features captured in the BEAST model, as well as at the end you have things like sign max, ratio min, and dominance, which capture other additional tendencies that didn't emerge as important in thinking about the random effects. So this is our set of 9 psychological features. I come to Noah's question of how did I pick which ones? Well, okay, no, I don't. Apparently, I give a concrete example first. Just to say, if you still don't have some intuition for what this actually means, you can consider this gamble. And this is the presentation format which I gave people the gambles in my experimental setup. This is very closely mirroring what was done in CPC 18, where you can see the expected value of this option on the right is higher than on the left. So if you were just going in accordance to expected value, you would have a tendency towards choosing option B. But if you see that expected value is higher because of these low probability, high outcome events, which means actually picking that option B that is the higher expected value, 90% of the time, you're going to be feeling regret because option A would have actually got you a better outcome because you're going to get a 3 and outcome A is going to be a 6. And so this is just one example of a feature that captures, if I were just attending to EV, I would pick B. If I were just worried about minimizing regret, I would pick A. And so these are what each of these features are endeavoring to capture is these different perspectives or heuristic valuations of the prospects that we see. So turning to exactly what I did. I took 50 problems drawn from the algorithm used to construct the problems for the choice prediction competitions. So this is this 11-dimensional space. I think this is one of the great strengths of the CPC work, that it has a clearly defined space. If we think about all the problems in non-replicable science, a lot of it comes from people picking specific edge cases without disclosing how they find those stimuli. So actually establishing a space and trying to look for generality across it, I thought was very interesting. But so I drew 50 new problems from this. So it's not something that's been featured in any of the CPC things, but it's from the same universe of types of problems. I then got 401 people off this platform ROI Rocket, which is still online data, but they're more careful in curating their samples than something like MTurk or Prolific. So this is quota match to get a representative sample. Then I had people answer these 50 problems twice. First, they did them as abstract gambles. So that's like the screen I just showed you. And then 1 week later, the same participants answered the same 50 gambles in a different random order, but this time they were expressed as financial choices. And I'll show you what that looks like later, with this 1 week time distance between the two. And in addition to this, I included individual difference measures in the design. So I measured things like Big Five personality, cognitive reflection, and so on. These are the new data that I collected. Then as to this point about setting up the analysis, the first question I wanted to probe is, does adding these random slopes onto psychological features improve our ability to predict people's choices in these types of problems? So I had 50 problems that each participant answered. For now, I'm just dealing with that first wave of data collection, the abstract choices. We're going to come back to the second wave later. I took a training set of 45 of those problems and then estimated random slopes using that data set and then predicted people's choices in 5 unseen problems. Now, this differs slightly from what was done in the individual track of CPC 18, in that people were tasked there with predicting specific held out choices of some individuals, but were given access to the aggregate performance of other individuals in those same problems. Here I'm holding problems completely out. So these have not been seen in any sense. And the model comparison I'm going to conduct, my baseline model is the following. I have a linear probability model where I have fixed effects for all of those features, the basic features, the naive features, and the psychological features, as well as having random intercepts for individuals. I'm predicting people's choices of option B. So the random intercept of, some propensity to pick the option B over A shouldn't matter. We include it there anyway. Now, the psychological models I'm comparing to include everything that's in that baseline model, plus 4 out of 9 of the random slopes on 4 out of 9 of the psychological features. Now, back to Noah's question of how do I pick those 4? I didn't pick a specific 4. I ran all 9C4 as 126 different combinations to be agnostic to this. I decided to put random slopes on 4 rather than all 9 at once, because it's only 45 choices I'm using to estimate these random slopes. And when I go to the CPC 18 data, I only have 27 choices to estimate these slopes. And so I thought it would be more advantageous not to try and estimate all 9 of them concurrently. And so we're going to see it doesn't really matter because a lot of the juice is driven by a couple of them. But so I did every combination here and didn't take any a priori view of what would work or not. We just let the data speak for themselves. So then all I'm doing is, once I've trained my random slope model on those 45 problems, for all individuals, I'm going to predict what they would do in the held out 5 problems, evaluate mean squared error, and we're going to do this 10 times. So this is just tenfold cross-validation. And if I do it with logit instead of linear probability model, it doesn't matter. I just picked linear probability model because sometimes logit can have some strange effects depending on the overall probability. Okay, so the first test that I'm going to do is, does adding random slopes to these psychological features just improve prediction? So here on this graph, along the x-axis, I just have my different specifications labeled 1 to 126 arbitrarily. They're just going to be ordered by the size of mean squared error improvement. And on the y-axis, I have the improvement in mean squared error. So we see, lo and behold, 125 out of 126 cases, adding these random slopes resulted in decreased mean squared error in the test set. Of those 125 success cases, 118 were statistically significant at p is less than 0.05. So we see pretty clear evidence that putting random slopes on these psychological features increases our ability to predict out a sample into these test sets. Within that, the best performing model had random slopes on these 4 variables. So the difference in the best estimate of expected value, exactly these 4 features. So if you return to actually the 4 tendencies proposed in the Beast model, we see it fall out perfectly here, that rather than having to kind of trust any theoretical reason that these are actually what's important, these are the main tendencies, this is the best performing model that achieves something like 8% decrease in mean squared error. Interestingly, and I can't give a clear interpretation for this, but it seemed to be more about probabilities than values. So if you remember, there were actually 2 different implementations of something capturing sign sensitivity, the expected value according to this, as well as the probability of a better sign. In all cases, it looks like these probability-based measures are more important. I don't know why that is, but I thought it was interesting. So We see clear evidence here that it is helping our predictive accuracy to add those random slopes. But you might have the question, how general is this? You know, you've got small data set, you're only looking at 50 problems, and it's one context. Random effects models can be very variable. How can I be sure that this model that's emerged as the superior model here is really something meaningful, that putting random effects on these specific features is really something I can walk away with as a takeaway? And so I turned back to the choice prediction competition data to run this exact same test, except I have to make a couple of modifications given the different structure of the data. So here there are 926 different participants. I'm just looking, remember, at the first time someone does a new problem. So actually people are doing these problems many times in a row in blocks. I'm going to say it's the same problem 25 times in a row. I'm just taking observation number one. And then for the second problem, you know, I'm deleting those 24 in the middle and I'm just taking the first observation of that problem. And so people did different sets of 30 problems here. So in my design, everyone did the same 50 problems. Here, people are doing different sets of 30. So I have to do this layering of setting up the cross-validation. I can't just hold out, you know, 3 problems. I'm actually holding out a different 3 problems for each set of people. Okay. It's a total of 27,000 responses when I've cut out those repetitions. Other than that, everything's the same. I'm setting up, I'm going to train my random slopes on 27 out of 30 of the problems. I'm going to predict into those held out 3. I'm going to repeat it 10 times and look at the reduction in mean squared error. We're asking the same question again, but just to see how robust actually is that takeaway of those are the features that you need to put individual sensitivities on to understand this. So I've got the same graph here. I just have my 126 different models along the x-axis. On the y-axis, I have the improvement in mean squared error. Here we see 100% of the time we got an decrease in mean squared error, but they're less likely to be significant. So here, 126 out of 126 are decreases, but only 17 of those are statistically significant. And you can say, why is that? My 2 hypotheses are that it's less data. So I only had 27 problems to train my random slopes. The second one is that they intentionally put paradoxes in these data. So they're just harder to predict because I've just drawn randomly from the space rather than kind of rigging the deck to put in the edge cases, whereas the edge cases are in these data. So I suspect that's what's going on, but I can't say for sure. That said, the top performing model here, the model that achieved the greatest reduction in mean squared error by putting random effects on those psychological features, exactly the same. So the fact that this one emerged at top winner very much seems to be non-random. It would be highly, highly unlikely to observe that if there wasn't actually something to this about that model specifically and their existing real individual sensitivities to those specific psychological features of the problems. If we look at this across the entire space, because I have the 126 models estimated in my data and estimated in CPC 18, I can take the mean squared error of those different random effects models and I can correlate the two. If we take that across all 126 models, the Spearman's rank correlation is 0.42. So it's still pretty good. It's not perfect. I thought this was quite high, given you've got data collected years apart. Some I think are in person in Israel. These are online data in the United States. They're different problems. There's a whole host of different things that are varying. But if we see there is substantial, if not, complete agreement in where it actually adds value to add those random effects to detect those individual sensitivities. But overall, the evidence is quite clear that we do improve our ability to predict individuals' decisions by factoring in these individual sensitivities to different psychological features. So moving beyond this, this is like 4 very interesting pages of the 2025 Nature Human Behavior by Ori and folks supplement, which is good for me because I think it's quite related to what I'm doing here. And, I still have to think about how to position the contribution relative to it. But say this approach of just using mixed effects regressions to detect individual differences and improve individual prediction of risky choices is very robust. You look, Ori compared it. This is with this big data set collected by Sudeep and these other folks for their 2022 management science. If you look in all those experiments, so that's a third set of experiments relative to mine and CPC 18 still, this using the features of Beast but having this mixed effects to allow for individual sensitivities seems to work pretty well. So I think on the whole, this approach is promising for getting good predictive accuracy whilst also accounting for these individual differences. Okay. Does anyone have any questions at this point? Great. We'll move on. So I've split the next part of the results, which I think are the really exciting part, where we go beyond thinking about prediction to actually what have we learned? What specific tendencies do we see? I split into two parts. I'm going to start by interpreting and talking about just this one best performing model. So I think trying to talk about all of the models at once can lose this concreteness and get a bit more confusing. Having talked about that best performing model, I'm then going to zoom out to thinking what general takeaways can we make from all 126 at once. There's substantial overlap, so it's not that I'm going to tell you one thing, then change everything, but I've chosen to divide the results in this way. So this is our best performing model, is putting random slopes on those four specific features, this little screen cap that I showed you at the start. It turns out, if I exit the for loop and actually dive into this model, really we don't need a random effect for this difference in the best estimate of expected value. This is a singular fit. I think it's come out there because I only have a few problems under ambiguity, and this is really dealing with those ambiguity cases. It turns out that's just not that important. But these other three features really are. So capturing that equal weighting heuristic tendency, that sensitivity to sign heuristic tendency, as well as this tendency to minimize regret. These are really the three psychological factors that we're going to spend some time diving into. So now we're returning to our financial data. So again, to remind you of the design, people answered 50 questions. They waited 1 week. They saw those same 50 questions, but now expressed as financial gambles in a different random order. So these data are entirely held out. We've not seen them. They are the same problems, but we've not had any access to them in training our models. And so they looked like this, just to give you a sense. Essentially the probabilities are exactly the same. The outcomes I've just times by 10 and put $1 on the front, but they remain the same ratios. And it's a pretty minimal investment setup. There's a company A and company B. It's not that it's varied massively. It's to say, in addition to this time delay, there is some contextual variance in the actual choices people are being asked. And so now the question is, if I take my best performing model, so putting random effects on these variables, I train it just on my abstract choices, and then I try and predict to look at the mean squared error in those same 50 choices again a week later as financial choices. What I get is a 2.4% decrease in mean squared error relative to a pure fixed effects model, and that's statistically significant, p 0.005. So these individual sensitivities I've estimated at time 1 are predicting into time 2. And so that tells us that they're not super context sensitive, and this small change of context here wasn't enough to nullify them, as well as it tells us that there is some time stability. If it were just that everything is driven by contemporaneous situational factors, I come into the lab, I'm happy, and so I'm just taking all of these risks, or I'm sad, so I'm not. If it was something like this, we wouldn't expect any additional benefit from these random effects in predicting into a different time period. I will note that this model was not the best model of predicting into those financial choices. So if I think of all the 126 options I have at time 1, predicting into those financial ones, of the models that did better, 85% of them had sign sensitivity. They had random effects on this B-bet sign. 88% had it on this P-bet unbiased. It's this equal weighting where that was not critical. For getting the best model of predicting those financial choices out of sample, that was not critical. But these two features really emerge as the ones where the random effects on them add the most idiosyncratic value. And that's pretty robust across every way I've cut these data, is the equal weighting is somewhat important. Those two are really the most important. But we can go
So,
beyond this. Yeah.
um, that's very cool. I have a question more broadly. How good can you predict even the fixed effects, just the fixed effects? How good can you predict the week later uh, results with this approach?
With my approach is something like point 0.2.
Uh, we, okay, so point two in mean squared error,
Yeah.
um, given that it's proportions, right? So, is there a way to interpret these? How good this is, or do you have some measure of how? I mean, how good this is relative to other approaches?
Yeah, I don't have clear benchmarks. That's something that, as I move to the next steps of this, I want to benchmark it relative to, prospect theory, relative to prospect theory, estimating individual parameters for this. That's work I still need to do, and I'm working out how to contextualize it. So no, I don't have a number I can give you. The mean squared error changes are around like point 0.2. It's not proportions, right? Because it's at the individual level.
Oh,
So I'm
okay.
always taking some predicted probability and differencing it from 0 or 1. Um,
I guess this should be some way to do what I mean. Even what's the mean squared error of random model? Uh, give it some context. But yeah, we can talk about that later.
Agreed. I definitely need to add some more benchmarks to be clear on the predictive results. I think the most exciting part is more the psychology that's underpinning it, but I agree that's definitely an important part for the ultimate paper that in
Yeah,
another.
just to put in the context, the 2.4 decrease in percent decrease in MSC, that's great, but maybe you can do much better with using a different model. So yeah,
I
okay.
hear you.
Yeah.
Thanks. So this is initial evidence that these things may be stable over time, that we may actually be detecting some property of how humans approach decision making, because if they had no stability over time, we wouldn't expect them to improve uh, prediction into these data a week later. But we can be much more specific than this and look at those individual sensitivities themselves. What is the test-retest reliability between them? So now if you think for each of these, if I train a model with all 50 choices in the abstract, and then I get my random effect. So each individual has some specific slope that is capturing their sensitivity to these variables. I can then do the same, but just using the financial choices. So it's the same 50 choices, but it's a week later, they're entirely disjoint data sets. The same people, but disjoint data sets. Now I can look at, person one had some specific weight on minimizing regret at time one and time two, and I can just look at those correlations to get some measure of the stability over time of these random effects. If I look at these, they're actually pretty good. So this difference in best expected value, as I said, the fit is singular. The standard deviation of this is essentially 0. So this we don't need. It's not capturing anything. But for these other three, you see this test-retest reliability of the random slope on minimizing regret of 0.6 is pretty strong. There's a lot that's going into this. This isn't some Likert scale where I've just said, do you like dogs 1 to 5? A week later, do you like dogs 1 to 5? There's a lot of choice data that's going into this that is used to ultimately estimate this parameter in conjunction with a whole bunch of other parameters, and we get a test-retest reliability of 0.6. To me, this is pretty strong evidence that we're detecting real psychological differences in the extent to which people are sensitive to these different psychological aspects of choices. So even the others, 0.52, 0.40, you wouldn't get this if there was nothing stable underpinning it. But this fourth feature that's really capturing that sensitivity to minimizing regret seems to be the strongest psychological difference that emerges. So I'm calling these individual sensitivities. That is just the random effect. So it is that person's regression coefficient for this specific factor. This is an individual sensitivity, but when we have those, we can now turn to thinking about individual differences. and trying to actually predict those individual sensitivities. So here what I'm going to say, if I take the weight for some individual on minimizing regret, can I predict that weight from other features I know about that person? To test this, I'm going to first have a pure demographic model where I try to predict that weight with these. So age, gender, education, household income, employment status, marriage status. I'm going to say if I just regress those regression slopes on these factors, can I predict well? Then I'm going to ask, do I improve my prediction of their sensitivity to minimizing regret by adding individual differences in personality, in cognitive reflection, as well as different measures of risk preferences? And so it turns out in all cases I do. So adding variables like cognitive reflection increases my ability to predict how sensitive an individual is to minimizing regret. And the R squareds with everything included, they don't get that high, but they show some potential for this. So if I'm trying to explain variance in people's individual sensitivity to regret, I can get to an R squared of about 0.2. I don't think that's our optimum. This just includes some individual differences I thought might be interesting, but I think we can do more. I'm going to move a little bit quickly because I've noticed time's going on and I don't want to overstay my welcome of talking. So turning to what can we actually do about this? Because of course, as well as thinking about adding explanatory value, we can see what are those specific relationships. So here, if I look, these are the regression coefficients of predicting these random slopes with these different variables. They're not correlation coefficients. This is from a regression where everything's included at the same time. And I've blanked out anything that's not statistically significant. So we see if I want to predict someone's sensitivity to which outcome will provide the better outcome more of the time if I do uniform weighting, I can see open-minded people are more sensitive to that feature. Agreeable people are less sensitive. More cognitively reflective people are more sensitive. I can do the same for each of the others. We see that there are consistently statistically significant relationships between these different individual differences. I can see people who are more extroverted, agreeable, and neurotic. All of those are negatively associated with being sensitive to the probability of a better sign of an outcome. Of course, in an ideal world, these would be obviously and easily face valid. You would have neurotic people, they're really worried about signs, they're really worried about regret. That is not what we're seeing. If you look, neuroticism is positively related to the sensitivity to the uniform evaluation and negatively to the sign or unbiased. So it's not that we look at this and it's obvious off the bat, this is exactly what's happening. It shows that those real stable individual sensitivities to psychological properties of the problem, we are able then to relate to other psychological tendencies. And so in addition to all this stuff, I also looked at can we predict these, this is all from the same regression, can we predict these with just these different aspects of people's preferences for investment that are used in industry? This comes from this paper Dan Goldstein has with Sharp and other people where they say these are industry risk measures. I don't know, I have no means of verifying this. But if you look at questions like, how likely are you to engage in different gambling activities? Or if your investment experiences some loss, do you have a tendency to sell it or will you wait it out? These things are also quite predictive of these individual sensitivities. So I view this as just further validation that actually what we're detecting in these random slopes is something real, something psychological that relates to people's general tendencies in the area of dealing with risk and uncertainty. So I'll pause for a moment to give intermediate takeaways. In fact, I think in the interest of time, I'm going to skip this slide and just go to thinking about robustness across 126 models. So I've shown you a few things so far. I'm now going to do the analogous analysis across all 126, and then I will conclude with what are the overall takeaways, which is we already saw that the top performing model in both my data and in CPC 18 is the same. We also saw that the Spearman's correlation of the mean squared error of those different sets of models is about 0.42. But if I look across all 126 models, so when different features are being included in combination with different others, which features emerge as consistently important to achieving superior predictive accuracy by adding random slopes? Regret is the one that emerges as by far the most important. In all of the most predictive models where you're adding a random effect and that's getting you extra predictive juice, regret is there. So that probability of achieving a better outcome is a really key factor. After that, the most robust is the sign, sensitivity to sign. And then that probability uniform feature emerges in some, but not all. So if you look at the most predictive models, regardless of what else is being included at the same time, regret is the strongest tendency that there are individual differences in. We then saw that my model, trained on 50 abstract choices, could improve significantly predictive accuracy in the financial choices, which Zori highlights I need to do more to contextualize, but that is a significant improvement. If we look at adding 4 random effects to any of those different variables in time 1, 98% of those models do better in mean squared error in the financial choices. 63% of the time it's significant. So we can see it's broader than just that one model I showed you. There are various ways in which we can detect some individual sensitivity that improves that out of sample prediction. And these test retests, before I showed you the test retest of just in that one model, if I look at it across all 126 models where sensitivity to regret is included, and I do that test retest, and then I average across them, we see a similar story. The random effects, the individual sensitivities to regret and to sensitivity to sign, these are pretty stable. Uniform a bit less so. In some cases, there's some stability for other features, so difference in best estimate of expected value and so on. And then finally, if we come back to this, thinking about actually interpreting these random sensitivities, we see here I looked across a whole 126 models and I deleted anything that didn't emerge as the same pattern in at least 90% of specifications. So just to make sure that something wasn't overly sensitive to what else was being included. And we see some of them go away, but we still see this broad psychological importance. Now I'll conclude with zooming out a little bit to think what really is the takeaway. Is adding these individual sensitivities on these random effects improves prediction. That emerges in almost all cases. That result is robust. The most important feature to add random effects on is this sensitivity to regret. Then it's this heuristic evaluation based on sign. We see that you can use these individual sensitivities to improve prediction in a new context, and also that they're stable over time. That's another robust result across every way you cut the data. Those regret and sign specifically, individual sensitivities are important. And then if we look at actually interpreting these psychological differences, so that was that last slide, but here I'm just simplifying it, is you can see open-minded people, meaning that they score higher in trait open-mindedness, are more sensitive to the probability of getting a better sign and the probability of getting a better outcome based on uniform valuation. Conscientious people are more and extroverts are less sensitive to regret and to sign. This you might expect about extroverts. That kind of comports with how we might view these types of people. It's less worried about regret and negative outcomes. And higher CRT people surprisingly are more sensitive to all of these. You might think if CRT is touted as some measure of rationality or something that's going to bring you more in line with EV, so you will not be as sensitive to these types of heuristic valuations. But here we see they're more sensitive to regret, to sign, and to uniform. So these are concrete takeaways that we have already. I still think we can do more to build on this, but already we see that those individual sensitivities that capture how sensitive we are to regret within this BEAST framework both help us with prediction and we can explain them in terms of common psychological tendencies. And so, future directions. Something I'm excited about doing next is trying to say, can I predict someone's random slope on regret solely from demographic factors and then use that fitted random slope to beat predictive accuracy? I can nearly do that already. I think with a new set of individual differences that explain more R squared in my random slopes, it's going to be possible. If you think about the implication of that, it's if I know some psychological features about you, I can think about how sensitive you're going to be to regret, and I can predict what you're going to do in unseen gambles, which has important applications, also psychologically very interesting. I'm curious about whether these are conscious or unconscious. So if I have someone who looks as if they're more sensitive to the sign, are they spending more time looking at the negative outcomes? Can I detect something that tracks this actually into their decision-making process? So I talked about moving towards that algorithmic level of the representations and processes people hold. Can I find some process evidence to get there? As well as can I expand this to factoring in feedback, as well as once you're in feedback worlds, adding more behavioral features. So I'm thinking of this 2026, what is it, PNAS or Nature Human Behavior or something by this group in Paris, who built on top of Beast to find more things like negative recency. Can you factor in individual sensitivities to those as well in this paradigm to continue building on it? But so with that, I've already talked longer than I wanted to, so I'm now open to questions and hopefully we can have a bit of a chat. Thank you.
Thank you. This is super interesting. And now, as you said, we are opening it to questions. So, Ido, I think you have a question. Please go ahead. We don't hear you.
Well, thanks. That was really interesting and not much, we didn't think about it. At least I did not think about it when we start working on that, but to really kind of move in that direction, and I can see now the value. Just to help you, I'm guessing what reviewer 2 will say, and Ori already mentioned that. So reviewer 2 probably going to say, yeah, but you could also do the same thing with prospect theory because regret maybe is correlated with a weighting function, and sign is regret with loss aversion. So probably to address reviewer 2, you will have to do the same thing by estimating the prospect theory parameter and see if you can do the same thing. Now, prospect theory parameter are correlated with 2 features, but our correlation is of course less than 1, especially in the case if you have 2 more than that the safe option have 2 outcomes, because so it will be really important to do if you have not done that. So this is one suggestion. Yeah, and yeah, so this is definitely what you have to do to help the reviewer 1, but I think the results are really interesting.
Thank you. Yeah, so Ori told me this in Spudum in September, and then, life got away from me. So I've got the code off him to estimate prospect theory and do this. I need to do it yet. So, I mean, despite working on it for 8 years, I'm embarrassed to say I have no manuscript for this work. It's work in progress. But I completely see that, there's no more convincing to do. I just have to do the work.
Yeah. Another thing for self-promotion is that after you do the prospect theory, you can translate your MSD score to what I call ENO, so you can say compare your prediction for how many average of how many other participants you can do to predict behavior better. But this is really not really important. The prospect theory is really what is important to show how you contribute over previous research. And there is a paper by Andreas Glockner and co-authors, which is part of the dataset that analyzed by he and Sudeep, that tried to look at individual difference in prospect theory. So you definitely want to compare them to what these guys did.
Thank you. Absolutely.
Yeah, so if there's no one else, I'll jump in. So of course I like this very much, as you know, and I've heard about that from you in Spudem. But one thing I can't remember if I asked you before, so you're treating pessimism as the difference in expected values thing. I think we had a different definition for pessimism. It was the difference between the minimal outcomes. Is this something that you've tried or it didn't work, or can you remind me?
Yeah, so I was going to ask you about this. The difference in minimums, I think, disappears from your work from 2017 and later, no? This is in the psychological forest, but then
Yes.
disappears in later work.
Oh, no. So in the nature of human behavior paper, so what we did is we defined this feature as both naive and psychological. So
Hmm.
it might disappear in one of the tables that's discussing psychological, but I think that's the definition that we use at least for the recent paper.
Gotcha. So I have tried putting random effects on the four naive features together, and I don't improve predictive capacity. So I guess you'd expect to have seen it in that test
Yeah.
together.
Okay. So you did try it. Okay. Thanks.
Sure.
I think it's kind of so the results of the sign and regret. It was also the strongest maybe in my analysis of the different data set of Sudeep's and Li Sheng's data set, right? Am I remembering correctly? You don't
I
know.
Yeah, I don't have it off the top of my
Yeah.
head.
Okay.
One of us should, but
Yeah. Okay. So it's nice that you replicate with a completely different. Well, not replicate. It's us that replicated it because you had it first, I guess. But for the yeah,
wow, I needed to
completely
get it in
different data
print.
set.
I needed to get it in print. I have to work out how to write that I'm building on your approach when I also want credit for it. But
No, I think the stuff that you can predict individual different with different with demographics and other individual difference measures, you can predict this individual tendencies is fascinating, and I would not expect that, as I told you. It's very nice.
I was a bit surprised at how strong the effect is. So I think my next moves are I'm going to run another study where I include more personality measures and another replication and try to increase the R squared of how much of the random effect I can explain.
Yeah,
So I think for me that's a really exciting part of it.
it's very cool. Yeah, I mean, yeah, I'm surprised with the effect, and I really like that it works.
Yeah.
Okay, guys, thanks for the fascinating talk. Unfortunately, the time is running out, so the formal part is now over, and I will stop the recording. And those who have to go can go. And Asher, thanks again for the great talk. And we will stay here for 10 or 15 more minutes with an informal discussion.
Sure. I like that you formally end the formality. Like we have to be licensed.